picture this. You're not a medical professional, right?
Right.
You have absolutely zero background in biology, oncology, pharmaceuticals, nothing. But your rescue dog, an 8-year-old Staffordshire Bull Terrier Shar-Pei cross named Rosie, has just been given a devastating diagnosis.
Oh, no. That's always heartbreaking.
Yeah, it's mast cell cancer. And it's aggressive. It's, spreading through her hind leg. And the veterinarians are giving her 1 to 6 months to live.
Wow. 1 to 6 months.
Exactly. And conventional chemotherapy has completely failed. Multiple invasive surgeries have failed to stop the spread. And, well, most people in this situation would just, prepare to say goodbye.
Yeah. I mean, what else can you do? You're out of options.
Right. But you happen to be a data analyst.
Okay.
So what do? You open ChatGPT.
Naturally.
You map her tumor's mutations. You use an artificial intelligence tool that literally just won the Nobel Prize to help build a completely personalized mRNA cancer vaccine.
That's wild.
And the punchline, the tumor shrinks by 75%, and your dog goes from barely being able to move to literally jumping fences.
That's incredible.
The scientists who helped synthesize the vaccine are just absolutely stunned.
I mean, it genuinely sounds like a piece of speculative science fiction, but this is exactly what happened. And it represents a fundamental seismic shift in how we approach the most complex biological problems on Earth.
Welcome back to What the Study Says. I'm Dr. Kai.
And I'm Dr. May.
Today, we are bringing you an independent investigation.
Right.
We're two doctors digging into the wild intersection of consumer AI, personalized medicine, and the 2024 Nobel Prize in Chemistry.
Right. It's a huge topic.
It really is. Our mission for you today is to dissect these sources. So, a fascinating, very real news report about Rosie the dog's customized cancer vaccine, alongside the official scientific background of the 2024 Nobel Prize.
Yeah, we want to understand how artificial intelligence has just fundamentally rewritten the rules of biology and, what this actually means for the future of public health.
Exactly. It's just a remarkable convergence of events. But to really grasp the magnitude of what happened with Rosie, we need to look at her owner, Paul Cunningham.
Right, because by 2024, Paul had spent tens of thousands of dollars trying to save Rosie from the skin cancer.
Yeah, fortune.
And the conventional treatments were, well, maybe slowing the tumors down a bit, but they simply refused to retreat.
But Paul brings a completely different toolkit to the table. Like, he has 17 years of machine learning experience. He's a data engineer.
Which changes everything.
It does. So he looks at this biological roadblock, and he doesn't see an insurmountable medical tragedy. He sees a data processing problem.
I love that perspective.
He actually told a newspaper, no worries, I'm a data analyst, and I'll figure this out with the help of ChatGPT. And he meant it literally.
And the methodology he executed was astonishingly sophisticated. Like, he didn't just type, cure my dog's cancer into a prompt box.
Right, because that wouldn't do anything.
Exactly. He used ChatGPT as a high-level research assistant to plan out a complex genomic sequencing strategy.
Right.
The chatbot essentially helped point him toward the Ramasiati Center for Genomics at the University of New South Wales.
And this is where he takes real-world action. He pays 3,000 Australian dollars to have Rosie's DNA fully sequenced.
Which is a big step.
It is. And the logic here is fascinating. He doesn't just sequence the cancer, right? He takes her healthy cells and compares them directly to her tumor cells side by side.
Oh, smart.
Yeah, he's looking for the microscopic spelling errors in the DNA, like the exact mutations where the cancer has hijacked Rosie's cellular machinery.
Right, and finding those mutations is crucial because he's hunting for something called a neoantigen.
A neoantigen.
Yeah, when cancer mutates, it often produces these abnormal proteins on the surface of the cell. And if you can identify those abnormal proteins, they act like a glaring red flag to the body's immune system.
Got it.
But the immune system needs to know exactly what that red flag looks like to attack it.
Okay, let's unpack this. Is this just a tech guy getting incredibly lucky with his pet? Or is AI essentially acting like a biological Google Translate that anyone can use to circumvent traditional medicine?
Well,
because having a list of genetic spelling errors doesn't automatically give you a vaccine, right?
No, exactly. And it's vital to clarify the specific roles of the AI here because it is certainly not magic.
Right.
ChatGPT was the orchestrator. It helped him read the literature, plan the research, and, iterate on the vaccine design. But the true heavy lifter, The engine under the hood that made identifying those red flags possible was a completely different AI called AlphaFold.
Ah, AlphaFold.
Yeah. Without AlphaFold, Paul would just have a spreadsheet of genetic mutations. He would have zero idea what physical shapes those mutations formed in the real world.
And that raises the million-dollar question. How did a data guy with a laptop know what those mutations actually look like in 3 dimensions?
Right.
The reason Paul could map those mutated proteins is thanks to a tool that literally just won the 2024 Nobel Prize in Chemistry.
That's so timely.
It really is. To really understand what AlphaFold is and why it's so revolutionary, we need to look at a 50-year-old grand challenge in biology.
It all starts with understanding what a protein actually is. Like, we often think of proteins as just a nutritional macro on a label.
Like protein powder, yeah.
Yeah, exactly. But in biology, proteins are microscopic machines. They're the ingenious chemical tools of life. If a protein is shaped like a pair of scissors, it cuts DNA.
Okay.
If it's shaped like a grappling hook, it grabs onto a virus. Form equals function.
And they all start out as a simple one-dimensional string of amino acids, right? Usually about 20 different types.
Yes.
And they're linked together like beads on a necklace. But to become that functional machine, to become the scissors or the grappling hook, that string has to fold up into a very specific, incredibly complex 3-dimensional shape.
Exactly. And in 1969, a scientist named Cyrus Levinthal pointed out a massive, almost terrifying paradox about this folding process.
What was the paradox?
He calculated that even a relatively small protein, just 100 amino acids long, could theoretically fold into 10 to the 47th power different shapes.
10 to the 47th. Wow. Put that number in perspective for you. 10 to the 47th power is astronomically large. It is vastly more than the number of stars in the observable universe.
It's huge.
So Levinthal realized that if a protein tried to find its correct functional shape by just randomly twisting and folding through all those possibilities,
it would take longer than the age of the universe to get it right.
Right.
Yet inside our cells, proteins do this flawlessly, millions of times a second in a matter of milliseconds.
It is completely mind-bending.
It really is. And Christian Andersen won a Nobel Prize in 1972 for proving that the one-dimensional string of amino acids contains the entire blueprint for the final 3D shape.
Okay.
But knowing the blueprint is there and actually predicting how it will fold are two very different things. For half a century, chemists tried to solve this prediction problem.
Because the traditional way to figure out a protein shape was agonizingly slow. Scientists used a technique called X-ray crystallography.
Oh, yeah, a nightmare.
Yeah, you basically had to take the protein, figure out how to freeze it into a perfect crystal lattice, and then shoot X-ray lasers at it.
Sounds complicated.
It is. By looking at the shadows it casts, the diffraction pattern, you try to reverse engineer the shape of the machine. It could take a researcher their entire PhD, years of labor, and millions of dollars just to map one single protein.
It was such a frustrating bottleneck that in 1994, researchers started a global competition called CASP, the Critical Assessment of Protein Structure Prediction.
Okay.
It was basically the Olympic Games for biochemists. Organizers would take a protein sequence whose shape had just been painstakingly mapped using X-ray crystallography, keep the shape a secret, and ask teams to predict the structure using only the amino acid sequence.
And for decades, the progress was incredibly painfully slow. The entire field was stuck at around 40% accuracy.
Yeah, they tried using massive supercomputers to run molecular dynamics simulations. They essentially tried to physically simulate the folding process in a virtual water solution, atom by atom.
Which takes forever.
Right. It took astronomical computational power just to simulate a few microseconds of folding for a tiny protein. It just did not scale.
Then the landscape shifted in 2018. Dimas Hassabis and John Jumper from Google DeepMind entered the CASP competition.
Oh, DeepMind.
Yeah. Hassabis had a background in neuroscience and had previously developed the AI that mastered the impossibly complex board game Go.
Right, AlphaGo.
Exactly. They brought an artificial intelligence model called AlphaFold to the protein problem. And they immediately bumped the accuracy up to nearly 60%.
Which is a huge jump.
People were definitely surprised, but 60% still isn't good enough for reliable, real-world scientific use. If you were designing a life-saving drug, you need about 90% accuracy to rival a physical X-ray crystallography experiment.
So they went back to the drawing board. John Jumper, who had a deep background in theoretical physics and protein simulation, helped overhaul the entire AI architecture. They abandoned the older neural network methods and utilized a relatively new AI breakthrough called transformer networks.
Hold on, before we go further, I'm losing the thread a bit.
Yeah.
A transformer network is the exact same underlying architecture that runs text-based models like ChatGPT, right?
It is, yeah.
How does a text prediction tool help fold biological proteins?
Well, what's fascinating here is that transformer networks are not just for text. They are incredibly efficient at identifying hidden patterns and contexts across massive amounts of data, no matter what that data is. For ChatGPT, it's words in a sentence. For AlphaFold 2, it's the evolutionary history of amino acids.
Interesting.
Yeah, the AI aligns sequences from different species and searches for parts of the protein that have co-evolved over millions of years.
Here's where it gets really interesting. If two amino acids always interact in a folded protein, they're inextricably linked. Let's use an analogy. Think of two amino acids physically touching each other like a lock and a key.
That is a perfect way to visualize it. If a random genetic mutation over 1 million years causes the lock amino acid to get deeper, the protein will break unless the key amino acid also mutates to get longer.
Right.
If the lock becomes negatively charged, the key has to become positively charged so they stay attracted to each other. Otherwise, the organism just dies out.
Or if one side mutates to repel water, the other side has to mutate to repel water so they can hide from the cellular fluid together.
Exactly.
AlphaFold looks at millions of these evolutionary lock and key pairs across different species. It realizes, every time amino acid number 10 changes, amino acid number 85 also changes. They must be physically touching each other in the final 3D structure.
Yeah, and by analyzing these massive evolutionary patterns, AlphaFold 2 creates a highly sophisticated distance map. It passes this map back and forth through its transformer networks, iteratively refining the spatial relationships until it arrives at a final, highly probable 3D structure.
And when they unleashed AlphaFold 2 at the 2020 CASP competition, they completely shattered the ceiling. They hit that elusive 90% accuracy mark.
Wow.
They effectively solved the 50-year-old grand challenge of biology. Suddenly, a computer prediction was just as good as years of expensive X-ray crystallography.
The impact was immediate and honestly profound. DeepMind didn't just hoard this technology. They used AlphaFold 2 to predict the structure of virtually all 200 million known proteins on Earth.
All 200 million?
Yep, every protein from every organism we have ever sequenced, and they made the entire database publicly available.
Over 2 million researchers from 190 countries have used it to study everything from antibiotic resistance to enzymes that can literally decompose plastic.
It's incredible.
It is a complete paradigm shift in how we read the machinery of biology. But reading the structures that nature provides is only one side of this 2024 Nobel Prize.
Right. If Demis Hassabis and John Jumper solved how to read protein structures, the other half of the prize went to a scientist who figured out how to write them from scratch.
Okay, writing them?
Yeah, we were talking about David Baker at the University of Washington.
While the rest of the world was agonizing over how existing natural sequences fold, Baker decided to completely reverse engineer the process. He built a software program called Rosetta.
Rosetta, okay.
Yeah, he wanted to design brand new proteins that had never existed in nature.
The field is called de novo protein design. For a long time, if scientists wanted a protein to do a specific medical or industrial job, they would take an existing natural protein and try to tweak it.
Right, modify what's already there.
Exactly. But Baker realized that the range of natural proteins is strictly limited by what evolution required for survival.
Baker has this incredible quote in the Nobel sources. He said, "If you want to build an airplane, you don't start by modifying a bird. Instead, you understand the first principles of aerodynamics and build flying machines from those principles."
That's a great analogy.
Isn't it? He applied that exact logic to biology.
His team used Rosetta not to predict shapes from sequences, but to input a completely novel, desired 3D shape and have the software compute the exact amino acid sequence required to make it fold that way.
But wait, if predicting the fold is already insanely complicated, how does the software calculate a sequence out of thin air to force a specific shape?
Well, it relies on the fundamental physics of energy states.
Okay.
In the physical universe, everything wants to rest at its lowest possible energy state. Water flows downhill to rest in a valley. A stretched rubber band wants to snap back to a relaxed state.
Right.
A folding protein is just a molecule trying to contort itself into the most physically relaxed, stable shape possible.
So it's like a ball rolling down a bumpy, jagged mountain. It's going to keep bouncing around until it settles into the deepest, lowest valley it can find.
Yes, and Rosetta acts as a map maker for those valleys. It uses fundamental physical principles like van der Waals forces and hydrogen bonding, which act like tiny microscopic magnets, to calculate how different amino acids will pull on each other.
That makes sense.
It optimizes the sequence so that the target shape you want is the deepest, lowest energy valley for that specific string of amino acids.
In 2003, Baker's lab achieved a monumental breakthrough to prove this worked. They created Top7.
Top7.
Yeah, it was a completely synthetic protein made of 93 amino acids. Its three-dimensional structure existed nowhere in nature. They designed the sequence on a computer, introduced that genetic code into living bacteria, and let the bacteria manufacture it.
And did it work?
When they checked the result using X-ray crystallography, it folded almost exactly as the Rosetta software predicted.
If we connect this to the bigger picture, the creation of Top7 proved that human beings are no longer confined to the chemical tools that biological evolution provided. We can act as molecular architects, custom designing microscopic machines to solve very specific human problems.
Baker open-sourced the Rosetta code, and the creations that have come out of his lab since are absolutely staggering. In 2017, they designed entirely new proteins that bind specifically to fentanyl, acting as microscopic environmental sensors for this synthetic opioid.
Wow. And by 2021, they had created geometric nanoparticles with proteins on their surface that perfectly imitate the influenza virus.
Really?
Yeah, these were successfully tested in animal models as a completely new approach to viral vaccines, potentially offering broader protection than traditional methods.
They are designing molecular rotors. They're building custom proteins that can change shape based on external signals to act as tiny, targeted sensors inside the human body. They are quite literally writing custom biological software.
Which brings us back full circle to Paul Cunningham, his dog Rosie, and the personalized cancer vaccine.
Right.
When you synthesize the predictive power of AlphaFold to read mutations with the incredible design potential of systems to write customized mRNA responses, you completely rewrite the timeline of medical research.
Paul took the list of Rosie's genetic mutations, ran them through AlphaFold to see exactly what those red flags look like in 3D, and wrote his own machine learning formulas to pick the most prominent target.
Which is brilliant.
He took what would normally be months of painstaking million-dollar laboratory analysis and condensed it into half a page of mathematical formulas.
And Professor Paul Thordarson, the director of the UNSW RNA Institute, actually took Paul's half-page formula and built the physical mRNA vaccine.
Just from that formula?
Yes. And within a week of the first shot, Rosie's tumor started visibly shrinking. This pipeline sequencing, AI modeling, and vaccine synthesis was compressed from years into mere months.
Professor Thordarson made a vital point about democratizing medicine. He believes this approach could eventually allow local, regional labs to design and produce custom therapeutics.
That would be amazing.
You wouldn't necessarily have to rely on massive, slow-moving pharmaceutical companies to push generic treatments through a bloated, decades-long pipeline.
It is an incredibly optimistic vision for the future. However, as independent doctors looking at this data, we have a strict obligation to evaluate the limitations impartially. We must look at the crucial caveats of Rosie's case.
Absolutely. First and foremost, this was a sample size of exactly one. One dog, one specific tumor. There were absolutely no controlled clinical trials involved in this process.
Right. Furthermore, veterinary oncologists know that mast cell tumors can, in some rare cases, shrink spontaneously on their own.
That's true.
While the timing of the AI-designed vaccine and the 75% shrinkage strongly suggests a causal link, without rigorous scientific controls and placebos, we cannot definitively state the vaccine was the sole reason for the remission.
And rolling this out to humans is an entirely different ecosystem. The regulatory framework for human medicine is appropriately strict to prevent harm.
For good reason.
Right. Human trials for personalized mRNA vaccines will require years of regulatory scrutiny, intense safety testing, and hundreds of millions of dollars.
Yeah.
Even Paul Cunningham stated very clearly to reporters, "I'm under no illusion that this is a cure."
He's realistic about it.
He knows the scientific limits, even though he firmly believes it bought his dog significant quality of life.
And companies are already heavily invested in developing personalized mRNA cancer vaccines for humans. The biological mechanisms are very real, but the primary bottleneck is shifting.
How so?
We're moving from the scientific discovery phase, figuring out how to build the drug, to the clinical validation and regulatory phase, proving it is safe at a mass scale.
So what does this all mean for you? It means the foundational code of life has been permanently cracked. We can read it with tools like AlphaFold, and we can write it with tools like Rosetta.
Exactly.
Artificial intelligence is no longer just a novelty generating text summaries or writing code for apps on your phone. It is generating the microscopic molecular structures of life-saving therapeutics.
We've crossed a threshold in human history. The design of complex biological tools is rapidly becoming a computational problem rather than purely a slow, manual laboratory problem.
Which leaves us with a final, rather provocative thought for you to mull over. If an amateur data engineer with a laptop can design a customized cancer vaccine for his dog using an open-source chatbot and a freely available Nobel-winning AI.
Are we entering an era of garage medicine?
Right. Are we moving toward a future where customized life-saving therapeutics are essentially downloaded and synthesized locally, almost like you would download a software update for your phone?
This raises an important question that our current regulatory systems are entirely unprepared for. Like, what happens to our traditional frameworks of medical safety when the code of life itself becomes open source?
It's a huge unknown.
How do you regulate a customized, personalized cure that was essentially invented by an algorithm 5 minutes ago?
It is a staggering concept to wrap your head around. Make sure to subscribe and share what the study says so you never miss a deep dive. From a data analyst facing a terminal diagnosis for his rescue dog to the Nobel stage in Sweden, we've seen how the invisible machinery of life is finally being brought to light. Thanks for listening.